David Smith here with one more flipped classroom math video. 3 tips before we start. First, remember you can speed up the playback if that helps you get through the video faster. Just make sure you understand and keep up with your notes. Second, you can pause the video at any time to catch up with your notes or think about the topics. Lastly, you can turn on the captions and watch my words go by on the bottom of your screen. Let's do a review of differential calculus. Now this lesson, this review lesson, is specifically tied to the International Baccalaureate Applications and Interpretation course, Year 2. And specifically, it references the Oxford University Press Chapter 12 book. So I put that up in the title here. If you're not in that course or not using that book, this is definitely useful, but the difficulty of the problems might be different from your course, and the types of problem might be different. So it's useful, but you want to make sure that you fill in any gaps for the course that you're taking. Okay, so derivatives, rates of change. This whole chapter is about rates of change. So let's back up a second and take a look at 2 functions. Here is a linear function, y equals mx plus b. The rate of change in this function is constant. It's a straight line. So the rate of change is the slope of that line. For every x that goes by, you're going to go up the same amount of y. So the rate is constant. So pretty cool. Easy to say the rate of change. Now let's take a look at this function. I'm sure you're familiar with the basic parabola, y equals x squared. What is the rate of change right here? And what is the rate of change right there? Is it bigger or smaller than there? We don't have a straight line. We don't have an mx plus b. So the rate of change is not entirely clear in a curved function. So this applies to quadratics, to cubics, to rationals, to exponentials, all kinds of functions. So this whole section, this whole chapter is dealing with finding rates of change for curved functions. So that's the overall context. Okay, back to my list. Here is your basic tool to find derivatives, called the power rule. And basically the way it works is if your function is some coefficient times x to some power n, then the derivative of that function is nax to the n minus 1. You take the n, multiply it by the a, so that's your na, and then you take the n and reduce it by 1. So that gives you the derivative of that function. Now why do we do that? It relates to tangent lines. So let's go take a look at some tangent lines just to get orientated to that. Okay, here is a curve, some kind of parabola, some kind of quadratic, and I've marked 2 points, one in black and one in red. Tangent line zooms along and it just kisses the function at 1 point, doesn't cross it, it just hits that function at 1 point. So I have this slopey tangent here and I have that horizontally tangent there. And you can find slopes of tangent lines all day long. Now here's the thing, the derivative function gives you the slope of the tangent line. So for whatever value of x you're interested in, you plug that in to your derivative function and it gives you the gradient of the tangent line. Now that's pretty cool because the gradient of the tangent line is the rate of change at that point. So this solves that question. When you want to know the rate of change on a curved function, it's the slope of the tangent line at that point. Different point, different tangent line, different slope, different rate of change. In case of a parabola, the rate of change is increasing, increasing, increasing from point to point. So there's no one rate of change for a parabola or for a quadratic equation. So f prime of x gives us the tangent's gradient. Now normal lines are kind of interesting. Let's go over to the graph. A normal line is perpendicular to the tangent line at that same point. So this normal line goes out at 90 degrees to the tangent line. And tangent and normal. So here we go. Normal lines, the slope for those is the negative reciprocal of the tangent slope. And if you recall from when we did parallel and perpendicular lines back in Algebra 1, Algebra 2, the slopes of those two, parallel and perpendicular, are related by the negative reciprocal. So if your slope of tangent line is, say, 4/5, then the slope of the normal line would be negative 5/4. So that's this. We're going to exploit that. Finally, differential calculus lets you do things with minima and maxima. We get to optimization problems. So with a curved graph, this is a minimum. Graph never gets below that, has to be higher at all times. Same thing with that one. If you have a parabola that's the other way, that's a maximum. So that would be the highest value that function can ever have. So maximums and minimums have perfect applications to real-world problems where you want to maximize something, like profit, or you want to minimize something, like cost. So that's where differential calculus hits the road and does some real relevant, real-life math. So the last point here is that at a minimum or a maxima, the derivative is 0. And let's zoom over to the graph. Here's my tangent line that's tangent at the vertex, at this minimum. Notice how the tangent line is horizontal. There's no rate of change. At that exact point, the function is not decreasing or increasing. So the slope of the tangent is 0. So we exploit that. We use that, we set the derivative equal to 0, and then we can find some things about the minima or a maxima, find out how to optimize something, and so on and so forth. So this is the whole territory. The rest of this is taking derivatives, doing algebra, and understanding word problems. All right, let's take a look at a problem. This is going to pull this together. We're going to do just about everything we talked about on that last big board. So for f of x equals 3x squared plus 4x minus 3, the slope of the tangent at point B, don't know what that point is, but we know its tangent slope is minus 2. Find point B. Now, we're not given the x or the y coordinate of B. All we know is the function and the slope of the tangent line, minus 2, but we don't even know where that is on the function. What are we going to do? Guess what? We take the derivative function, set it equal to 2, and we can find x. And then we can plug x into the original function and get the y value, and that will tell us what point B is. So your first step here, take the derivative of the original function and come right back. Okay, so here's our derivative. Power rule on this term, power rule on that term. The constant goes away. So now my derivative function is 6x plus 4. So now what we do is this thing spits out 2. It's the negative, it's the function that gives us the slope of the tangent line at any point. So we can plug in the slope and solve for x, just like this. 6x plus 4 equals negative 2. Now we're going to solve for x. So we get 6x equals negative 6, x equals negative 1. So the x-coordinate of the point at tangency, where the slope is minus 2, the x-coordinate is negative 1. Now if we want the y-coordinate of point B, we plug the negative 1 back into, pause, think about it, which function, this function or that function? Tell me what you think. Okay, if you said this function, that's not right. This function gives you slopes of tangent lines. This function relates the x-coordinate to the y-coordinate. We found the x-coordinate of point B, so we plug it back into the original function to get the y-coordinate. So pause the video and do just that. So here we are. I just plugged my negative 1 into my function up there, did my plug-in step, reduced it down, and I get negative 4 comes out of the original function when you put in negative 1. So that means my point B is negative 1, negative 4. So to summarize, this function has a tangent line at point B. Don't know what that is, but we know the slope of the tangent line is negative 2. So we can take the derivative, set the derivative equal to negative 2, do the math, find the x-coordinate of the point of tangency, then plug that x-coordinate back into the function, get the y-coordinate, and we have point B. Okay, not done. Second prompt. We've got B, we know it's negative 4, or negative 1, negative 4. Now we're being asked to find the equation of the normal line. So let's go over to this graph again and just take a look. This could be our tangent. Actually, this is not right. That's got a positive slope. So really what we have is a tangent line somewhere over here, and we have a normal line like that. So remember, the tangent line, the normal line is at 90 degrees to the tangent line. So we have a point. This point is also on the normal line because we're looking, always on, it's on the normal line because where the tangent and the normal meet, they meet at that point. So what are you going to be able to do? We need to find the equation of the normal line. You have enough information. Pause the video and write down what you have. Okay, here's what we have. We have the slope of the tangent line. So that means the slope of the normal line is the negative reciprocal of that, which is positive 1/2. There's the slope. Here's a point that's on the normal line. If you have a point and a slope, that defines the line, and you can come up with the equation. So go ahead, pause the video and do those steps and come back. Okay, let's see how you did. Y equals mx plus b. I'm just going to plug in my point. So that's my y point right there, equals m. We know the slope of my normal line is 1/2 times x, which is -1, plus b, which we don't know. That's the only thing we didn't know. So now we just did our plug-in step. That reduces down to b is -3.5. So the slope of our normal line is y equals 1/2 x minus 3.5. All right, here's another fairly tough kind of an IB problem if you're not well practiced, especially in this first step, the entry point into the problem. Oftentimes that takes critical thinking, and if you can't get there, you really don't know what to do. So let's take a look. A right cone has a slant height of 8. Find the height and the radius such that volume is maximized. Now already that seems daunting. We need to find two variables, and we only know one distance. That's like, well, where do I start? So think about this for a minute. Maybe look at the formula booklet, take a look at some of the formulas for cones, and come back when you have a little bit more information. Okay, here are the two things I get. You've got a nice right triangle in our cone. You got to always look for those, and remember your trusty friend, the Pythagorean theorem. So I can write h squared, that's not a negative, let's just get those out of there. I can write h squared plus r squared equals 8 squared, or 64. So that's a nice statement that we can make, that's true. And then I pulled out the volume of a cone formula. The volume of the cone is 1/3 pi r squared h. Now, I need that because I'm trying to optimize the volume. I'm trying to maximize that. So I knew right from the get-go that that formula is going to be part of this problem. Now, think for a minute. What are we going to do? Basically, we did this before. We have to do some conniptions and a substitution so we can have an equation with one variable, take the derivative, and go on. So pause the video. What are you going to do to get that? Okay, so I would love to be able to sub something in for r in this equation so I can solve for height. So here we go. I got r squared. I move my h squared over to the other side, 64 minus h squared. R is going to be root 64 minus h squared. So now I have an r that I can sub in to this function and rearrange and get something I can take a derivative of. So pause the video and do that. All right, check this out. So what I did is I just went ahead and substitute my r, my root 64 minus h squared. I put that in for r right there, so it's squared. Nice thing, because the root of something squared is just the something. So I rearranged, put my h in front. So now I have 1/3 pi h times 64 minus h squared. Now, is that the form that we can take a derivative of? Nope, we don't have anything. We need to get it to be a one term, an na or a ax to the n power. So I want you to pause the video and do the algebra on this to get this into something we can take a derivative from. All right, here we go. So I brought this up from the last board here, and basically we have 1/3 pi h times 64 minus h squared. So this is just a straight up distributive property. You got to keep track of all your terms, but that's all we're doing. We're going to multiply 1/3 pi h times 64 and 1/3 pi h times negative h squared. So this one times 64 is just 1/3 64 pi h. I'm just leaving these all together. 64 divided by 3 doesn't come out to be a good number, so we're just going to leave it like that. And then 1/3 pi h times negative h squared just gets the h up to the third power, so we have negative 1/3 pi h. Now, these two terms, yeah, they're a little jumbly-uppy, but they are both in the right form to take a derivative of that. So I want you to pause the video and find v prime of h, I guess is what we're doing. Yeah, v prime of h. So pause the video, do that. All right, actually this ended up being pretty simple. The h is my variable, so I have h to the 1. So I multiply that over. That doesn't change anything. I have 1/3 64 pi, h to the 0 goes away. So now I combine my fraction to get 64 over 3 pi. That's my first term. And then this one, I bring my 3 down, multiply it by negative 1/3. That becomes negative 1. So there's my negative. The 1 I don't say. I leave my pi right where it is, and I reduce my h to h squared. So that's pretty cool. And notice that I just brought my pi's along. Way easier than tracking all these decimals and worrying about where to round. You could put pi into your calculator when it's time to calculate something. Okay, so pause the video, think about what is the next step. Okay, we're dealing with our volume equation. The volume is a function of this. So to maximize, what we want to do is set our derivative equation to 0. That's a 0 slope for the tangent line. That means the function is at a max or a min. Okay, so solve that for h. All right, here we are. I set it equal to 0. I moved my pi h squared over to the other side, so it's positive. Got all my negatives out of there. Now I'm going to divide through by pi, and guess what? That's going to cancel this pi away. So I never needed to put pi in anywhere because I canceled it in this step. So again, leave your pi's in there until you absolutely have to use the value of pi, because most times it's going to cancel. So now I have 64 over 3 equals h squared. So h is just going to be the square root of 64 over 3, which ends up being 4.62. Cool. Now pause the video, think real hard. Are you done? You're not done. It said find h and r such that volume is maximized. We have h. You need r. So pause the video, think back, look in your notes. There's a handy way to calculate r. You need to do that. Okay, I went back in my notes. We solved for r so we could substitute this in for r in our volume expression. So we know that r is 64 minus h squared, the square root of that. So I just plugged in my r, 4.62 here, squared. I did my math and I get r equals 6.53. So we are done from the prompt. What I would be doing if this was my problem and I was doing this on a test is I'd reread the prompt to make sure it didn't ask me for that volume, because that is a logical finish to this problem, but I'm not going to do that because it's not in the prompt. Last problem. Check it out. This is from the realm of physics. So we're going to chuck a ball off the top of a cliff. Ball's thrown from the top of a cliff. The height is given by this equation. You'll notice that's a quadratic equation. Cool. Okay. Prompt here is find the maximum height. Now, back in Algebra 2, we would do this by converting this equation to vertex form, and that would tell us what the maximum height was. And I think it's a little bit more algebra intensive. Calculus is a more elegant way to answer the same question. So, I want you to pause the video and think for a minute, what is your first step in this problem? All right, your first step is to find the derivative function of our original height function. So pause the video and take your derivative and come back. All right, pretty straightforward one. Power rule works on these two. Constant goes away. So here is my derivative function. Pause the video. What step comes next? All right, let's see how you did. Next step is to set the derivative equal to 0. So I just popped a 0 in there. Here's my derivative function. I moved my minus 0.1x over here, divided through by 0.1, and I got x is 15. Now that's the x value at the maximum. The y value is the height. So we have one more step. That step is to find y. Now pause the video. You got to do a plug-in. Make sure you do the plug-in in the right place. So think about that, come up with your answer, and then come back. Okay, so you don't plug this value into your derivative function. This is what gives you slopes of tangent lines. You take your x value and you plug it into the original function, and that will give you the y value when we hit the maximum height. So pause the video, do just that. All right, I did my plug-in step, put my 15 in for x in my original function, crunch those numbers. I get y is 93.25 units. So I wasn't strictly, I didn't follow protocol with this problem. I didn't give you units to start, so we don't know what those units are by the end. So to be super careful, I put units. They could be inches, feet, meters. We just don't know. So that's the maximum height. Now, if you wanted to be sure that that was the maximum height, pause the video and tell me what you would do next. Okay, so our next step, let's verify it's a maximum. We use our trusty sign diagram to do that. I brought down my derivative function because we're going to need that. But before I turn you loose on that, let me remind you, with a quadratic, we can tell by inspection whether we have a min or a max. Basically, if the quadratic term, the term with a squared on it, is negative, we know we have a parabola that opens this way, and that makes that a maximum. So we already know that just by inspecting the equation. However, if you see a prompt that says show that, verify that, prove that, you're going to need to go to your sign diagram just to satisfy the IB and get all the points for that question. So here's my sign diagram. We put our x value in the middle, so we had x is 15, and then we picked two values on either side of the x that help us figure out whether the function is increasing or decreasing. Pick easy numbers, so I'm going to pick 10 and I'm going to pick 20 there. And so now go ahead, pause the video. I'm not going to prompt you with what you need to do. Pause the video, do that, and come back when you've verified that indeed a maximum happens when x is 15. Okay, let's check out and see how you did. So I'm plugging in my 10 in my derivative function. I crunch some numbers. I stop right here because I have -1 plus 1.5. I know that's going to be positive. So we know the function is increasing all the way up to 15. Good sign. And then finally, let's do y prime of 20. And we get 0.1 times 20 plus 1.5. Negative 2 plus 1.5. We know that's negative. So the function is decreasing. So we have a plus here on the left side of 15 and a minus on the right side, and that shows us that the function is going like this and then like that, and that gives us a max right there. So now you've shown that this point at x equals 15, height 92 point something something, that is a maximum on our function, so that's the max height. All right, I know we finished up with some word problems about maximization and minimization and optimization, but all of those problems have a fundamental understanding of the function and its graph. So I want to finish this video by reviewing that context. If you can hold that in your mind, it's very possible to do all of these complicated problems because they all relate back to this. Okay, so in black, there's my function. It's a curve. Okay, so rate of change on that curve changes from point to point. I can take a tangent, find a tangent line at a point. That gives me the rate of change at that point on the function. The slope of the tangent line is the rate of change. So what we do is to find the derivative function is we take the derivative of the original function, and that function gives us the slope of the tangent line at A or B or C or any point along the function. So that's the primary purpose of the derivative function. Finally, shifting to normal lines, these, we didn't do too much with them, we just characterized them. We found their slope. That's the, first off, normal line is perpendicular to the tangent line. The slope is the negative reciprocal of the tangent line slope. Okay, so now things that we did. We found the equations of the tangent and the normal line. We have this point, and we have the slope of the tangent, and we have the slope of the normal. So a point and a slope is enough to define a line. A little algebra there, and you have your line equations for both the tangent and the normal. We also set the derivative function equal to 0 to find minima or maxima. And the reason that is that when the derivative is 0, the slope of the tangent is 0. So you have a situation like this, where the tangent is, that would be a maximum, and the same thing like that, that would be a minimum. The tangent lines are horizontal at either the max or the min, and therefore they have a 0 slope. So that's what helped us find the max or the min. And then finally, we verified with our trusty sign diagram. And make sure you know how to do that, because you will almost certainly see that prompt on a test, either in my class or in another class. Now that you've watched the video, take a moment to write down any questions so you can bring them to our next class. Always remember, you can watch the video again to deepen your understanding. If you enjoyed the video, please click like and subscribe.